All right, so chapter 11 starts the idea of talking about organic chemistry. There's one element we really have not talked about much at all this semester. What element is that? This would be called the compressed structural formula, okay? Where instead of showing all the bonds, we just say there's 3 hydrogens on this carbon, 3 hydrogens on this carbon. We assume that the 2 carbons are connected. Okay? Does that make sense? We're good?
What did you call it again?
This is called a condensed or compressed structural formula. Condensed or compressed structural formula. This is expanded. These are both structural formulas. This one shows all the bonds. This one doesn't show all the bonds. Okay? Let's do this one together. This is butane. Contains 4 carbons. Okay? Let's look at it. Predict the shape. We're not going to worry about shapes. Okay? Around each carbon, I want you to give me the compressed or condensed structural formula. Can you do that? Should we do it together? Let's do it together. The way I do it is I circle each carbon and whatever is attached to it. And then I'm going to condense each part, okay? This has 1 carbon and 3 hydrogens, so it is CH3. What do you think comes next? CH2, because there's only 2 hydrogens here, right? And then CH2 again, and then CH3. Anybody see anything, any pattern developing here? The ones on the end have 3 hydrogens. The ones in the middle have 2, don't they? Okay. Make sense? We're all happy so far? Good, because you won't be in a little while.
I have a question.
Go ahead.
In terms of comparing the condensed structural formula with the molecular formula,
Yes.
how do you tell the difference from looking at them? I mean, how do I know this isn't just labeled another structural,
We're going to talk about isomers in a few minutes and different shapes and different structures you can get from the molecular formula. There are different ways that you could take C4H10 and draw different structures. Okay? And we're going to show that in a few minutes. This structure, as it's drawn, is represented by this condensed formula. Now,
okay, so the molecular formula is C4H10.
this molecular
And
formula,
this is
but it does not necessarily mean it's butane. There are other possibilities, and we're going to get there. Okay? We'll get there. Now, alkanes are the simplest organic compounds. They contain only carbon, hydrogen, and single bonds. So they're hydrocarbons with only single bonds. They're called alkanes. Now, we're going to practice naming some alkanes because I think that it's good for you guys to learn something. It helps you know something about the structure to be able to name some of these compounds. Now, alkanes are hydrocarbons with only carbon-carbon single bonds. They form continuous chains. Some of them have branches. We'll get to those in a minute. The names of alkanes end in A-N-E. Alkane ends in A-N-E, okay? And this chart is in your book. Chart 11.2, what page is that on? 364. Has a name for the first 10 alkanes. There's methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. I want you to know for the next test, the final exam that we take, right? The last day class, I want you to know at least the first 6. You have to know the names of the first 6. That's going to be helpful as we go forward to be able to name stuff. Okay? So you got to know methane, ethane, propane, butane, pentane, hexane. Fair enough? Peachy?
Peachy.
Okay. So, here's one. This is butane. How do we know it's butane? Because it has 4 carbons in the chain. The longest carbon-to-carbon chain in here is 4 carbons. That means it's butane. Okay? Does that make sense? Now, somebody in the other class said, you know, I just wrote the condensed structural formula for this a minute ago, and I would write it like this. And somebody in the other class said, so Dr. Powell, you're leaving out these dashes in here. Yeah, when you do on mastering, leave out these dashes. If you put the dashes in, it'll count it wrong. I don't know why the slides want to put these dashes in here. When you put the dashes in here, it's kind of like a hybrid between expanded and condensed formula. Get rid of those dashes. Write it like this, okay? Make sense? Butane would be CH3, CH2, CH2, CH3. The other formula that we can write, I don't like that they do this, is we can draw a skeletal structure. The skeletal structure for butane looks like this. Every time there's the end or there's a point, that implies that there is a carbon on here. This is a carbon, this is a carbon, this is a carbon, and this is a carbon. So if I want to draw the skeletal structure for hexane, what would it look like? Skeletal structure for hexane would be starting out here. 1, 2, 3, 4, 5, 6. That's hexane. And what do we know? The ones on the end are CH3s. The ones, oops. The ones at the points are CH2s, right? Does that make sense? The ones at the end are CH3s. The ones at the points are what? CH2s, okay? That's just a really condensed way of drawing a structure for it. And I don't know, some people like drawing squiggly lines like that. Because in the other class asked, does it matter how you draw it? No, I could draw hexane like this. It doesn't matter, okay? By convention, they're normally drawn like that, but this is also acceptable. So, the one thing to remember about single bonds is that they are free to rotate. Think about, anybody ever looked at like a Matchbox car or something? You have Matchbox cars when you're little? You look at the wheels on them? How are the wheels attached to each other? With a little axle in between, right? Just a rod, really. And what happens to the tires? They're free to rotate like this, aren't they? Well, a single bond acts like a rod like that between the two atoms. It rotates like this. And you might say, well, who cares about that? Well, it's going to be important later on, okay? So single bonds are free to spin. And that's why you can draw it like that as opposed to drawing it like that up at the top. Because things are spinning all the time, okay? That will change when we talk about double bonds, okay? Now, and here's some of their other structural formulas, right? See how here they have butane, and they have it drawn in a bunch of different configurations, right? You can draw it in a straight line, you can draw it like that, you can draw it like that, you can draw it like that. Doesn't matter. There's 4 carbons there in each one of them. Doesn't matter the orientation of them because they're free to rotate, okay? Now, can you give this is the expanded structural formula for, let's give the name of this before you guys give me these 2 things. What's the name of this? Who said it? Over here. It's pentane, right? Why pentane? 5 carbons, right? So it's pentane, there's only carbon and hydrogen, there's 5 of them, it's all single bonds, it's pentane. Now give me the molecular formula, the condensed structural formula for it, real quick.
C5H12.
C5H12 is the molecular formula, right? And the condensed structural formula, CH3, CH2, 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 CH3, right? CH3 is on the ends, and 3 CH2s in between. Okay? And you say, well, that's kind of boring. That's really not that exciting. Well, we're going to talk about doing some other stuff with it in just a second. Okay? Can you give me the condensed structural formula for these two? If you have your book open to that chart, it should be pretty easy, huh? Ethane is the second simplest one, right? Ethane has 2 carbons, so it's CH3, CH3, there's nothing in the middle, right? And then heptane is, how many carbons in heptane? 7. So 2 CH3s and how many CH2s in between? 5 CH2s in between, right? I can sit here and draw it, but this is going to be a mess. That's what they look like, okay? So 5 CH2s in between. Now, go a little bit further. Some alkanes aren't just long chains, they're actual ring structures. Where look at the 2 carbons on the end, they get joined together. Now, these compounds are called cycloalkanes. They form rings. So there's no beginning and end, okay? Now, in the other class, I asked them, why can I not do that right there? Well, let's erase that. What if I just join, it looks like these 2 carbons just get joined, don't they? Why can't I just join those 2 carbons like that? Because they already have full octets, don't they? So what do they have to do in order to be able to join like that? They share electrons, but what else do they have to do? They both have to lose a hydrogen. So note that here's my straight chain, my propane, and it's C3H8. The cyclo form of propane, they're both propane, right? They're both propane, but the cyclo form has 2 less hydrogens on it because they can't join together, right? They have to lose 2 hydrogens, okay? Now, there's 4 on this slide right here. In the other class, I'll point out these 2 over here, cyclopropane and cyclobutane, we can make them in the laboratory. Well, I can't, but some people can. Cyclopentane, they don't exist in nature at all. Okay, it has to do with the strain, and it's just not possible. These 2 guys over here, cyclopentane and cyclohexane, do exist in nature. Okay, they are very common 5- and 6-member ring structures, and we're going to talk a lot more about ring structures when we talk about sugars. Okay. So, can you give me the name for each of these 2 guys here? Why don't you guys work on it, we'll do it together real quick. All right, so what's the first one? Everybody got octane? 1, 2, 3, 4, 5, 6, 7, 8, right? So it's octane. Where do you find octane? Anybody use any octane today? Huh? When you're driving. Where do you use it when you're driving? It's in the gasoline. That number that you see on the gas pump, it's an octane rating, right? How much octane is in the gas? Right? Y'all knew that, didn't you? No. Who knew that? 3 people, that's it?
I didn't think.